This is a presentation on the foundation design for the Emirates Twin Towers presented by John O'Donnell, James Walsh, Christopher Martin, and Jacob Crist. The paper outlines the geotechnical investigation process undertaken during the foundation design of the Emirates Twin Towers in Dubai. One of the towers is an office at 355 meters and the other is a hotel at 305 meters. The office tower is currently the 8th tallest building in the world, while the hotel is the 17th tallest. The site plan is laid out on a 200,000 square meter area. The designers used a triangle plan to design the layout for the two buildings. The foundation system for both towers involved the use of large diameter piles in conjunction with a raft. Raft foundation is a thick steel reinforced concrete slab which covers the entire contact area of the structure like a thick floor.
The soil profile of the site was obtained by drilling a series of boreholes at a depth of 15 meters. These boreholes provided preliminary geotechnical data which revealed layers of sand or silty sand overlying very weak sandstone. However, for this project, the preliminary data was inadequate, therefore a comprehensive investigation was carried out, and this involved the drilling of 23 more boreholes to a maximum depth of about 80 meters. Standard penetration tests were also carried out at nominal 1 meter depths in the upper 6 meters of each borehole, and then at 1.5 meter intervals at the standard penetration test value of 60 was achieved. Looking at the borehole information, it was found that the stratigraphy was relatively uniform across the whole site, so it was considered adequate to characterize the site with a single geotechnical model. The investigation revealed 7 main strata and their average elevation relative to the Dubai municipality datum. Figure 1 is a representative diagram of these borehole drillings.
The design parameter for the foundation was based off the fact that the relatively good ground conditions promoted the usage of a piled raft system for both tower foundations. To qualify for this decision, the following tests were performed. Standard SPTs, permeability tests, pressure meter tests, vertical seismic shear, wave testing, site uniformity, borehole seismic testing, classification tests, unconfined compression tests, point load index tests, chemical tests, drain direct shear tests, and odometer consolidation tests. Test results concluded no variation in seismic velocity, uniaxial compressive stresses from 0.2 megapascals to 4 megapascals, average angle of internal friction is 31 degrees, cyclic triaxial tests allow its maximum stresses up to 930 kilopascals. Design parameters included importance in the fields of ultimate skin friction of the piles, ultimate end bearing resistance of piles, ultimate bearing capacity of the raft, and the Young's modulus values of these soils for both the raft and the pile behavior under static loading.
The pile foundations of both towers were designed using a limit state approach. The piles were designed so that RS and GS were both bigger than S, where RS is the design structural strength, RG is the design geotechnical strength, and S is the design action effect. Also, to take into account the effects of repetitive loading from wind, another criterion was made in which N times R of GS is greater than SC, where N is the factor assessed from geotechnical laboratory testing, RGS is design geotechnical shaft capacity, and SC is maximum amplitude of wind loading. For each tower, 18 load combinations were analyzed, 1 load set for the ultimate dead and live loading, 4 groups of 4 loading sets for various combinations of dead, live, and wind loading for the ultimate limit state, and 1 loading set for the long-term serviceability. A computer program called Geotechnical Analysis of Raft with Piles, GARP, gives us the sediment of soil as well as the transverse, longitudinal, and torsional bending moments of each node of the raft. It also gives the contact pressures below the raft and the vertical loads on each pile. In addition to GARP, the simplified boundary element program deformation analysis of pile groups was used to obtain the required input values of the pile stiffness and pile-to-pile interaction factors for GARP, and for computing the overall lateral response of the foundation system. Both GARP and DEFPIG were used for the ultimate limit state, with undrained soil parameters for the wind loading cases and with drained soil parameters for the dead and live loading cases.
Pile load test program results. Installation of 3 test piles near locations to each tower were installed. 3 meganewtons on a 0.9 meter test pile compression test and tension testing. Pair of reaction piles 12 meters apart with a crossbeam. 3 tests were performed. Static tension test included results finding maximum predicted load being 4.7 meganewtons, while actual load ended up being 5.5 meganewtons. Cyclic tension tests concluded foundation rotations under repeating wind loading could be subjected to an excess 25% of the ultimate static uplift capacity. And lateral load test concluded measurements predict a reversal of direction at 3.5 meters due to change in ground stiffness beyond the reduced level at 4 meters. The fact that actual capacity exceeded the predicted value was significant because the values of the ultimate skin friction used for these predictions were well in excess of the values commonly used for board pile design at the time in Dubai.
The geotechnical and structural designers altered the number, depth, diameter, and locations of the foundation piles numerous times during the design process. In the final design, the piles were primarily 1.2 meters in diameter and exceeded 40 or 45 meters below the base of the raft. The maximum settlement and maximum angular rotation under the worst loadings were calculated for both towers. The average maximum settlement was 183 millimeters, and the average maximum angular rotation was about 0.0038 degrees. The fact that this analysis does not predict collapse indicates that the main geotechnical design criterion was satisfied. That is, the reduced foundation resistances clearly exceed the worst ultimate limit state loadings. This can be seen in Table 1. The maximum settlement and maximum angular rotation under serviceability loading conditions were calculated for both towers as well. The average maximum settlement was 136 millimeters, and the average maximum angular rotation was about 0.0027 degrees. Although the computed values are relatively large, they nevertheless satisfy the design criterion set out in the serviceability limit state. Thus, the overall foundation systems were assessed to be satisfactory from the viewpoint of serviceability. Figure 2 shows the contours of the settlement for the hotel tower after 24 months as computed for both towers. The predicted settlements show a dishing pattern, with the settlements near the center of the building being significantly greater than those near the edge of the foundation. During the design process, it was found that the performance of the foundation was not greatly affected by raft thickness. Therefore, the design team decided to use 1.5 meters of raft for the final design. For the pile design, the maximum axial force, lateral force, and bending moment were computed so that the piles can be analyzed from the standpoint of the structural design, where it was found that the largest axial forces were developed in the piles near the corners and in the 2 of the core piles. The number of piles reached their full geotechnical design resistance, but the foundation as a whole could still support the imposed ultimate design loads. Combined with the moments developed by the lateral loading, the load on some of the piles fell outside the original design envelope. To address this problem of overstressing, they decided that it was best to increase the number of 1.2 meter diameter piles from the original 91 to 102 for the hotel tower, and the number of piles was increased from 68 to 92 for the office building. A seismic hazard assessment was carried out to predict the probability that an earthquake will occur in a given geotechnical area within a given window of time. Because of the lack of detailed information on likely earthquake time histories, the potential for site amplification was estimated simply on the basis of site geology. On this basis, the site was assessed to have a relatively low potential for ground motion amplification. However, the grading curves of the soils and the presence of uncemented sands near the ground surface suggested the possibility of liquefaction during a strong seismic event. The overall risk of liquefaction was assessed on the basis of the liquefaction potential index, and consequently there appeared to be no need to consider special measures to mitigate possible effects of liquefaction with the upper uncemented soil layers.
Measurements of tower settlement were only available for a limited period during construction. These measurements were compared to predicted settlement measurements as seen in Figure 16. These predictions were based on an assumed rate of construction and a rate of settlement computed from three-dimensional consolidation theory. As seen from the figure, the measured settlement was significantly lower than the predicted settlement. There are 5 possible reasons for this discrepancy, the first being that the settlements may have occurred prior to commencement of the measurements, the second being the time load pattern may have differed from the assumed pattern, the third being that the rate of consolidation may have been much slower than predicted, the fourth being that the effects of the pile interaction within the pile raft foundation may have been overestimated, and the fifth being that the stiffness of the ground may have been underestimated. The first of these 2 possibilities were considered least likely, while the last 2 were considered the most likely. When the DEF-PIG program was used to derive the interaction factors originally used, it had assumed that the soil between the piles and the soil around the piles had the same stiffness, and that the rock below the piles had constant stiffness. In reality, the ground between the piles is likely to be stiffer than the soil near the piles, because the level of strain within the rock below the pile tips is likely to increase significantly with depth because of both the increasing level of overburden stress and the decreasing level of strain. Since this was assumed for all piles, the smallest error can cause a rather large inaccuracy in calculated settlement. To account for these wrong assumptions, the ratio of modulus of the soil between the piles and the soil near the piles was increased to 5, and the modulus of material below the piles was increased from 80 to 600 MPa.
This project utilized modern methods of in situ and laboratory testing as well as advanced methods of foundation analysis. The site was characterized more completely than is usually possible with many projects. Since it was such a substantial project, the design process was complemented by a comprehensive program of tests. Despite all these tests, there were still discrepancies about the amount of settlement that would occur. Measured values during construction were only about 25% of the predicted values. Possible reasons for the significant discrepancy were investigated, and it was found that at least some of the differences could be attributed to the conservation assumptions made in deriving the pile sediment and interaction factors that were used in the piled raft analysis. The Emirates project involved close interaction between the structural and geotechnical designers in designing piled raft foundations for 2 complex and significant high-rise structures. The interaction therefore promotes the development of effective and economical foundation and structural designs.